Dear students, in this video we are going to study about the cyclotron, its principle and working, the force acting on a current carrying conductor which is placed in a magnetic field, the force between two long parallel current carrying conductors, and the definition of ampere. So let us study about the device called a cyclotron. What is a cyclotron? It is a device used to accelerate the charged particles to gain large kinetic energy. It is also called as high energy accelerator. It was invented by Lawrence and Livingston in the year 1934. What is the principle on which the cyclotron works? When a charged particle moves perpendicular to the magnetic field, it experiences magnetic Lorentz force. This picture shows a cyclotron which was invented by Lawrence and Livingston. So this is how a cyclotron works. It has two Ds, and the source of protons is kept at the center of the Ds. And as the fields are applied, these protons go in a circular path, increasing its radius and coming out with high energy. So the construction is like this. The schematic diagram of cyclotron is as shown, and the particles are allowed to move in between two semicircular metal containers called Ds, which are hollow D-shaped objects. The Ds are enclosed in an evacuated chamber, and it is kept in a region with uniform magnetic field controlled by an electromagnet. The direction of magnetic field is normal to the plane of the Ds. The two Ds are kept separated with a gap, and the source S, which ejects the particle to be accelerated, is placed at the center in the gap between the Ds. The Ds are connected to high frequency alternating potential difference. Now let us see how it works. Let us assume that the ion ejected from the source S is positively charged. As soon as the ion is ejected, it is accelerated towards a D, let it be D1, which has a negative potential at that time. Since the magnetic field is normal to the plane of the Ds, the ion moves in a circular path. After one semicircular path inside D1, the ion reaches a gap between Ds. But at this time, the polarities of the Ds are reversed as we are applying an alternating current. They are reversed so that the ion is now accelerated towards D2 with a greater velocity. For this circular motion, the centripetal force on the charged particle Q is provided by the Lorentz force. So this expression for the centripetal force mv squared by r will be equal to magnetic force QVB. From this we can find out the radius of the circular path taken by the particle. So it's given by r equal to mv by bq. As this q and b, e, q and b, they are constant, m is also a constant, therefore r will be directly proportional to the velocity. The radius will be directly proportional to the velocity. Therefore, from this equation, we find that the increase in velocity increases the radius of the circular path. And this process will continue, and hence the particle moves in spiral path of the increasing radius. Once it reaches near the edge, it is taken out with the help of a deflector plate and allowed to hit the target. So this is a reflector plate dp. Therefore, the ion will be hitting the target with high speed. The important condition in cyclotron operation is that when the frequency f at which the positive ion circulates the magnetic field must be equal to the constant frequency of a optical oscillator F oscillator. This is called as resonance condition, and from the equation 3.60 we have that the oscillating frequency equal to bq by 2 pi m, and the time period of oscillation is given by t equal to 2 pi m by bq. The kinetic energy of the charged particle is given by half mv squared, that's equal to q squared b squared by q squared b squared into r squared by 2m. But there are certain limitations of using the cyclotron. Let us see what they are. The first one is the speed of ion is limited. The electron cannot be accelerated as it will gain mass. Uncharged particles cannot be accelerated. So these are the limitations of cyclotron. Then we can study about the force acting on a current carrying conductor which is placed in a magnetic field. When a current carrying conductor is placed in a magnetic field, the force experienced by the conductor is equal to the sum of Lorentz forces on the individual charge carriers in the conductor. Let us consider a small segment of conductor which has a length of dl and area of cross section as A, and the current passing through it is I. So this is the current carrying conductor which is kept in a magnetic field having a length A and cross sectional area A. The free electrons drift opposite to the direction of current, so the relation between current I and the magnitude of drift velocity Vd is given by the expression I equal to NEA Vd, where Vd is the drift velocity, area of cross section A is area of cross section. And if the conductor is kept in a magnetic field B, then average force experienced by the charge, that is in this case the electron is the conductor, is given by F equal to minus E into Vd cross B. If n is the number of free electrons present in unit volume, then n equal to n by V. This capital N is the number of free electrons in small element of volume V. That's given by A dl. Hence, the Lorentz force on the elementary section of length A dl is the product of the number of electrons and the force acting on each electron. So that is given by Lorentz force is given by dF equal to minus En A dl into Vd cross B. The current element in the conductor is given by IDL equal to minus En AVD dl. Therefore, the force on the small elemental section of the current carrying conductor is given by this expression at dF equal to IDL cross B. Thus, the force on a straight conductor carrying current, which has a length L placed in a uniform magnetic field B, is given by the expression F total equal to IL cross B. This is involving both magnitude and direction. So in magnitude, the expression can be written as F total equal to BIL sin theta. And if a conductor is placed along the direction of the magnetic field, the angle is given by theta equal to 0. Hence, the force experienced by the conductor is also 0. But if the conductor is placed perpendicular to the magnetic field, then the angle will be about 90 degrees. Hence, the force experienced by the conductor is maximum, which is given by total force equal to BIL. Now let us see what is Fleming's left-hand rule. When a current carrying conductor is placed in a magnetic field, the direction of the force experienced by it is given by Fleming's left-hand rule, as shown in this diagram. Actually, here we are spacing out our forefinger, the middle finger, and the thumb of the left hand such that they are in three mutually perpendicular directions. If the forefinger points in the direction of magnetic field, here, this is the forefinger which points the direction of magnetic field. Then the middle finger in the direction of the electric current, then the thumb will point in the direction of the force experienced by the conductor. Therefore, the thumb will show the direction of the force experienced by the conductor, which is placed in the magnetic field and in the electric field. Then we are going to study about the force between two long parallel current carrying conductors. For that, let us consider two long straight parallel current carrying conductors which are separated by a distance r, and that is kept in a medium pair in this diagram. The I1 and I2 be the electric currents passing through the conductors A and B in the same direction, that is along the Z direction, like this. The net magnetic field at the distance r due to a current I1 in the conductor A is given by the expression V1 equal to minus mu naught I1 by 2 pi r into I vector, unit vector. So from the thumb rule, the direction of magnetic field is perpendicular to the plane of the paper and inwards. That is along the negative I direction. Then let us consider a small element length dl in the conductor B at which the magnetic field B1 is present. From the equation 3.66, the Lorentz force on the element dl of the conductor B is given by this expression df equal to mu naught I1 I2 dl by 2 pi r into j unit vector. Therefore, the force on dl of the wire B is directed towards the conductor A. So the element of a length dl in B is attracted towards the conductor A. Hence, the force per unit length of the conductor B due to current in the conductor A is given by this expression F by L. equal to mu naught I1 I2 by 2 pi r into j unit vector. Similarly, the net magnetic induction due to a current I2 in the conductor B at a distance r in the elemental length dl of conductor A is given by the expression B2 equal to mu naught I2 by 2 pi r into I unit vector. From the thumb rule, the direction of magnetic field is perpendicular to the plane of the paper and outwards, that is along the positive I direction. Hence, the magnetic force acting on element dl of the conductor A is given by this expression df equal to mu naught I1 I2 dl by 2 pi r. Therefore, the force on dl of conductor A is directed towards the conductor B. So, the length dl is actually attracted towards the conductor B as shown in the figure. Like this here. So, when the current in both the conductors are in the same direction, they will attract each other. The force acting per unit length of the conductor A due to the current in the conductor B is given by the expression F by L equal to mu naught I1 I2 by 2 pi r j unit vector. Thus, the force between two parallel current carrying conductors is attractive if they carry current in the same direction. So, if the current in the conductors are in the same direction, then there will be a force acting between these two conductors, F and F. The force between two parallel current carrying conductors is repulsive if they carry current in the opposite directions, as shown in the figure 3.56, like this. So, if the current flowing through the conductors are in the opposite direction, it will be like this. They will experience a repulsive force. So, from this expression, we can also define 1 ampere as that the constant current which when passed through each of the two infinitely long parallel straight conductors kept side by side parallelly at a distance of 1 meter apart in air or vacuum causes each conductor to experience a force of 2 into 10 power minus 7 Newton per meter length of the conductor.